Okay, welcome back to part 2 of the calculus videos for day 68. Now we're moving on to evaluating definite integrals. And if you recall, definite integrals require antiderivatives. So I'm going to talk through a few of these example problems. You can also look at the other examples that I have completed on this page, and hopefully that will jog your memory and get you well prepared for the test that we take on Wednesday. So in number 12, we see that we're evaluating this definite integral from a lower boundary of 0 to an upper boundary of 5, and we have the equation here. Now, if you're really comfortable with antiderivatives, you can probably move forward and find the antiderivative from here. But me, I like thinking about these in coefficients along with power rules. So I'm going to rewrite this function. And it's going to look a little bit like this. We'll take the integral from 0 to 5, and this negative sign with a denominator of 2, I'm going to rewrite that as negative 1/2, and then that leaves me with x squared plus 3 times x minus 7 over 2. And this integral is being evaluated with respect to x. And again, this just helps me see my antiderivatives just a little bit more clearly. We're evaluating this integral from 0 to 5. Oops, I guess I don't really need that anymore now that I'm going after the antiderivative. Once I identify the antiderivative, we'll evaluate it at the upper and lower boundaries. So the antiderivative in this case will be equal to this negative 1/2 acts as a coefficient for the time being, so I'll leave that one alone. And we have x to the third power divided by 3. That's the antiderivative of x squared. And then we have this coefficient of 3 that multiplies by x squared over 2. And this requires a subtraction of 7/2 times x plus c. And all of this will be evaluated between the values 0 and 5. Now this vertical bar again just tells us that what we'd like to do is evaluate this antiderivative. One time we're going to replace the x's with 5. In fact, that's what we'll do first. And then we'll subtract from it the same antiderivative evaluated with zeros in place of x. Now evaluating with zeros does make the work just a little bit easier, but so does the use of a calculator. So I'm going to set up mine off screen and then just record the final result when I'm finished. Okay, so again, with the two separate calculations computed, we'll get our end result after subtracting the two. Now, if we have the TI calculator available to us, then we can enter the entire expression all at once. And so this group of questions, or this expression here, is the antiderivative evaluated when x is equal to 5, and then I subtract the antiderivative when x is equal to 0. So I have both of those, and again separated by the subtraction sign. So when I press enter here, this tells me what the area under the curve would be. Now I do not want you to use a TI calculator on the test tomorrow that has the CAS enabled to it. So you likely won't see the fraction result, and instead you'll see the decimal result. And if you're using any other TI calculator like an 83 or a 30 or something like that, it too would produce the result in decimal form, and that would be fine for our test tomorrow. Additionally, if you were to do this problem and simplify each step individually, if you don't want to enter the whole thing all at once, that's fine, and you too would end up with an answer that looks like this. The area underneath the curve between an x value of 0 and 5 is approximately negative 0.83 repeating. I'll demonstrate my process through number 14. This time I'll do so without commentary. And here's the expression that I would need to take to the calculator. Again, we found the antiderivative. Negative x squared turns into this. 6x turns into this. 9 turns into this. You may have noticed that I rewrote this 6 times x squared over 2 as just 3 times x squared. That's because I recognize that 6 divided by 2 is just 3. That's just a small shortcut that I took along the way. And when I evaluate this using a calculator, I see the end result negative 2/3, or again with a decimal, negative 0.6 repeating. Moving on. And in this example, I ended up solving it without a calculator at all. Found the antiderivative for each term in the original, evaluated the antiderivative when x was 4 and 0. When x was 0, that whole section of the expression essentially canceled itself out, and I was left with the opposite of 4 squared, which was negative 16, plus 4 came out to be negative 12. Let's try another. And again, I made it to this point without the use of a calculator. There was a result of 0 that I know I would have encountered had any of these x values been set to 0. I also caught a small mistake that I made here when I first calculated the antiderivative. Fixed that along the way. And I'm now at the point where I need to add together negative 1/6 with 3/4 and then subtract 1/2. I could go to the calculator to obtain this, and in doing so I find that the result is 1/12, or approximately 0.083 repeating. So let's take a look at one more example. This time I'm going to rewrite this integral before I move forward with it, and I'm going to write this as 4 times x to the negative third power with respect to x. That'll help me understand the power rule just a little bit more clearly. So when I compute the antiderivative, I now have x to the negative second power divided by negative 2 plus c, and this will have to be evaluated from an x value of 2 to 3. And again, got to this point without using a calculator. Found the antiderivative, x to the negative second power divided by negative 2. Now this leading coefficient of 4 and the negative 2 will reduce to another leading coefficient of negative 2. That's 4 over negative 2. That led us there. And each x value is evaluated at the exponent of negative 2. Well, that's just like squaring the number and placing the result in the denominator. So this came out to be negative 2 over 9, and this one came out to be negative 2 over 4. So I'm at the point now where I'll just go to the calculator to combine these two rather than worrying about finding a common denominator. And the result here comes out to be 5/18, or approximately 0.27 repeating.